Today, we're going to be talking about some more repercussions of talking about multiple particles in quantum mechanics instead of just one. Today, we're going to look at something a little bit more important. Last time, we were talking about the atom and how it's affected by the fact that an atom can have multiple electrons now instead of just one, and there can be multiple protons in the nucleus. Although, that's a story for another time, as they're basically all concentrated into one little group by the strong force. So you can essentially treat it as one giant proton, and there's no trouble there. But there's something more important than atoms, more important than molecules, in fact. Entire solids. Any macroscopic solid, like this chalk over here, contains at least an Avogadro's number of atoms, if not more. So, how do we deal with such large amounts of atoms, which in turn means such a large amount of electrons? Well, that's what today will be spent discussing. First things first, let's assume that we just have an electron solid. It's a solid where a bunch of electrons are just bouncing around. If you can say they're bouncing around because they don't have any actual tangible position. So it's going to be a bunch of electrons that don't interact with one another, spreading their probability distribution across this giant nasty cube. In effect, the wave function for this will basically just be the wave function for one electron bouncing around in an infinite square well, but repeated as many times as there are electrons inside. So that gets pretty boring. But we still haven't actually solved the infinite cubic well, so let's do that really quickly, because we'll need it for our second layer of approximation. So what is the infinite square well in reality? Well, the infinite square well will just push you away anytime you try to come out, no matter how much velocity you come into it with. Which means that there must be an infinite amount of potential being applied at the border. The potential is going to have to look like the infinite square well that we used a while ago. Infinite walls on the outside so that anything within is constantly stuck. So that means that there's got to be an infinite barrier everywhere outside this little rectangular prism. So let's say there's a barrier from 0, x, well no, let's say this is the free spot, 0, y, ly, 0, z, lz, and within this free spot, the force and hence the potential is 0. And anywhere outside it, the potential is infinite, of course, to prevent anything from escaping. So now we have a good model of what the infinite cubic well looks like. Can we actually solve for, the solutions? Can you take a guess at what the solutions are going to look like? Well, recall that the Schrodinger equation is always written as the Hamiltonian psi is equal to E psi for some energy E, and the Hamiltonian in this case is very simple. Minus h bar squared over 2m nabla squared psi plus u psi is equal to E psi. Of course, within the well and outside the well, the wave function is going to be 0 because, of course, the probability distribution has to be 0 outside the well. There's no way the particle can end up outside the well, which means this has to be 0, which implies this is 0. So outside the well, the wave function is 0. But inside the well, well, this term goes to 0, and I think you can imagine what happens. If you break this down, well, okay, let's break it down into xx, yy, zz. You'll quickly notice that you can isolate each of these individually. You can get that minus h bar squared over 2m x double prime is equal to ex. You can get that minus h bar squared over 2m y double prime is equal to ey. then you can get that minus h bar squared over 2m z double prime is equal to ez. So, quite easily, you can show that, hold on, what's the actual constant going to be? The x function is going to be e to the I something something, so this is going to be over 2me. Yeah, this constant is fairly familiar. So it's going to be e to the I square root of 2me over h bar x. And yy is going to be similar.
Don't go that deep, I cannot capture that.
And zz is going to be similar. Which means that at the end of the day, the total solution should be fairly simple, right? Psi is equal to, well, inside the cube, or the rectangular prism, I don't know, it's going to be e to the I square root of 2me over h bar times x plus y plus z. And of course, outside the cube, it's going to be 0. So of course, now we have to actually normalize it. And we also have to take into account initial conditions. Remember that the corner of the cube is not actually in the cube. We said that before. These are not less than or equal to signs. They are strictly less than signs. So the corners are not inside the cube, which means that the ball cannot ever hit the corner, which means that the wave function at the corner has to be equal to 0. So what does that tell us? Well, I mean, along any plane where x is equal to 0, the wave function has to be 0. Along any plane where the y is equal to 0, the wave function has to be 0. Along any plane where the z is equal to 0, the wave function has to be 0. And that sets a bunch of, if we want a continuous distribution, which we definitely want if we want this to mean anything, we definitely need psi of 0, ab, or x of 0 has to be equal to 0, y of 0 has to be equal to 0, and z of 0 has to be equal to 0. Where x equals 0, y equals 0, and z equals 0. E to the I square root 2me over h bar. This is not the whole story. The real solution would be something like a trigonometric linear combination, an, or let's just call it a, well, it's going to be for x. So ax, sine square root of 2me over h bar x plus bx cosine square root of 2me over h bar x. And notice that, I mean, if x of 0 is equal to 0, what does that tell us? Well, sine of 0 is equal to 0, so this disappears. But cosine of 0 is not 0, it's 1. Which means that if this whole thing is equal to 0, bx has to be the one that's equal to 0. So that means the actual solution looks something like ax sine of the square root of 2me over h bar x, or y, or z. And not just that, remember that it's got to be 0 with the other corner too. It's got to be 0 when x is equal to Lx. So x of Lx has to be equal to 0. Which implies that, well, the square root of 2me over h bar multiplied by Lx has to be equal to n pi for some integer n. which sets a limit on how big Lx can be. And of course, that's also going to set a limit on how big Ly can be and how big Lz can be. They're discretized this way. N has to be an integer in this expression. So that tells us these solids can only be of specific sizes. That's very interesting. So now that also, of course, tells us about the volume of these solids. Now, so far, this is just a solid of a bunch of particles bouncing around, not even interacting with one another. Can we even call it a solid? It's more like a gas trapped in a massless box. So let's try to expand that out. Maybe what happens if we add in a bunch of protons? In a solid, the atoms, and so the protons, are relatively stationary. The protons just stay at the center of the nucleus, and the nuclei aren't moving. And in most solids, we have a crystal structure. You might recall seeing one of these funky things in chemistry. I don't know how to draw these. I'm not a chemist. A totally regular structure where all or molecules are bonded and equally spaced. This is a cubic lattice, and I've already made it go out of control. No, it's not supposed to be connected that way. You know what? I'm not here to be a chemist. And so on and so forth. We have these sort of crystal lattices where the atoms are evenly spread. Now, of course, they're not actually evenly spread because outside this box, there are no atoms, or the atoms that are there are a lot less dense, or they have some different properties. The solid does not go on forever. Those edge effects will have a pretty big effect on us, but we'll wait till later, and we'll see why later. So, what do we do with this? Now, what I'm going to do is take what we call a Dirac comb. Yes, he was very fashionable. Dirac's comb is surprisingly sharp. Surprises me how he didn't cut his head with this. Because it's just a bunch of delta functions. Regularly sprinkled at intervals. I mean, then again, he made the delta function himself. It's literally called the Dirac delta function. So maybe this is what he found comfortable to comb himself with. Who knows? So, this is the Dirac comb. And it's essentially the model that we're going to be using for these guys. Mostly because we're assuming these electrons now... no. Gotta be a better one. These electrons never escape the proton they're orbiting around. They stay in their atoms forever. And of course, that's not true. There's the whole reason why bonds exist. But for now, we're going to assume all these atoms are stationary and only interacting with themselves, not one another. And so these electrons are going to be hopelessly rolling in these small Dirac comb spaces. This is the potential that we're going to be using. And so this potential function, which is just a bunch of infinite cubic wells, I drew them as square wells here, but in reality, the potential function will look a little bit more like this. A little bit scary, isn't it? Especially when you realize these are infinitely sharp. No, it doesn't actually look like that. It would look something more like this. So when you have something like this, this is what electrons are dealing with. They're basically being kept in their own small cubicles, each trapped in here. And so, I mean, the solution to this is basically just the Schrodinger equation for a hydrogen atom repeated over and over and over. Now you might ask, well, what happens if there were heavier atoms? Why don't you draw interaction term? And it turns out when you have this interaction term in here, because of how weird the position operators and the position operators get when you have totally indistinguishable particles like electrons, because of how weird these become, it is totally impossible to get an analytic solution to the lithium atom or the beryllium atom, even the helium atom. Even if we have 2 electrons and 2 protons, and I think 2 neutrons, but they're basically dead weight. This is not simple enough to be analyzed perfectly. There are some approximations, but they're beyond the scope of what I plan to do in this series. So for now, there is strictly no discussing heavier atoms. Hopefully we'll make an episode on it in the future. For now, I want to get to something also very interesting, and something that also requires heavy approximation. Oh, there's another one. But it's interesting to us. You know why? Thermodynamics is interesting because its alternative name is statistical mechanics. It's time to talk about the quantum state of a configuration of particles. Let's say we have particle 1, particle 2, and particle 3. Not to be confused with thing 1, thing 2, and I don't think thing 3 exists, so we'll ignore it. What are you doing? Put your shoes on. Okay. We have 1, we have 2, and we have 3. So, let's say that with what we did in the past, because of what we know now, their energies the sum of the square of their energies has to be discretized. Well, it has to be, I think, h bar squared, pi squared over 2m squared. I don't exactly remember the specifics, but some constant c times n squared for some integer n. So, in this case, maybe it could be 243, and c could be 1. Nobody knows. But whatever it is, a lot of the time, there are multiple ways to solve an equation like this. I mean, even with a squared plus b squared is equal to c squared, sometimes if you have like 3, 4, 5, and 5, 12, 13, and you multiply 5 by 13, that's 65. Suddenly, you now have 39, 52, 65, 1 Pythagorean triple, and 25, 60, 65. Boom, another Pythagorean triple. You have 2 possible configurations that could satisfy the total energy of 65 squared. So, if there are 2 possible configurations, and not just 2, think about it this way. I mean, addition is commutative, so in total it could be 4. Particle 1 could have psi 39, and particle 2 could have psi 52. Particle 1 could have psi 25, and particle 2 could have psi 60. Then, particle 1, particle 2, you can just swap the orders. And bada bing, bada boom, you already have 4 possible states. The question now is which one of these is the most likely? Now, thermodynamics totally throws off that question. Hopefully, we'll be able to talk about it sooner or later. But if there's absolutely no entropy, no thermodynamic energy in the equation, these four are all equally likely. Or are they? How does this change when we're dealing with indistinguishable particles? And does it change when we're dealing with fermions versus bosons? Well, it's time to talk about probability and combinatorics. So, let's suppose that we have a bunch of possible combinations that could work. One combination, has 3 values that are the same and 3 values that are distinct. One has 2 values that are the same and 4 that are distinct. One has 5 values that are the same and 2 distinct. Showing how many there are of each is a problem unresolved by number theory. But showing the probability of each one, once you know them all, is something very much resolved by probability theory. So how do we go about it? Well, with indistinguishable particles, it's actually unexpectedly easy. All you have to know is that, you don't really care about the permutations of the particles. Reality has to be the same, whether they're in the same order or they're not in the same order. You know they can't, and you also know they can't ever share the same quantum state, which means this guy and that guy are out of the picture for indistinguishable fermions. Bosons are a little bit more tricky. So, at the end of the day, the number of possible arrangements comes down to a simple factorial for however many particles there are in the set. Meanwhile, with bosons, things get a little bit more tricky. How many ways are there to arrange this? It is one way that probabilists have devised in order to count how many different ways a bunch of particles can be separated into a bunch of different groups is through the stars and bars method. Or, let's say, with the circles and lines method. Let's say I have 6 circles and 3 lines. Then I can randomly arrange the lines any way I like within the circles. Now, I can treat the lines, which are supposed to act as separators, into the 3 groups as their own combinatorial object instead of just a division. We can essentially say the number of ways of arranging the lines and the circles is just going to be, 9 factorial for the total number of objects. We know that the particles are indistinguishable, so 6 factorial, and 3 factorial for the number of bars. So, these numbers still become very large very quickly. So, how do we deal with this? How do we get around having to deal with the 10 to the 80 particles that are in the universe and having to take, a factorial of them, or even the 10 to the 23 particles that are in a single crystal? How do we get around the fact that there are so many atoms? Trying to calculate 10 to the 23 factorial would crash any computer. Lucky for us, there's something called the Stirling approximation, which gives us a pretty good idea of how big a factorial is. N factorial is approximately equal to n over e to the n times the square root of n times a constant found by Stirling himself, which is why he gets the credit to be 2 pi. Actually, this was originally invented by de Moivre, which means de Moivre has been officially robbed of the name of an identity twice now. I mean, once with Euler's identity, which he originally discovered in nearly exact form, and second for this identity, which he also discovered in nearly exact form. Poor de Moivre. But oh well, we're not here to talk about him. So this approximation tells us a lot, especially since the square root of n basically pales in comparison. The Stirling approximation allows us to make very quick and easy estimations on how big pretty much anything is. For example, 10 to the 23 factorial, I mean, it's the square root of 2 pi times, well, you have n over e, that's 10 to the 22 times 10 over e. Now, I mean, e is about 3, so this is basically 3 times 10 to the 22. I mean, pi is about 3. Yeah, I'm acting like an engineer here. So this is basically 2.5. And what's in the power? 23. And what's in the square root? Well, this is just going to become 10 to the 11.5, which is basically 3 times 10 to the 11. Bada boom, bada bing. Suddenly I have, well, 2.5 is not too relevant. You can just estimate it as, well, what is this? 10 to the 22.5. And so whatever's in here is bound to become, well, 10 to the 22.5 to the 23, just 10 to the 22.5 times 23. And so you can see that the 10 to the 11 pretty much pales in comparison. So pretty much immediately, you've already obtained bing, 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 6. Let's just go with 11. 500. Yeah, 7.5 times 10 to the 528. That took me like 2 minutes by hand. Meanwhile, you can't even guess what it would look like from just using the factorial. Certainly, I wouldn't have guessed it to be 10 to the 528. So, as you can see, this method of counting, statistical mechanics, opens up to an absolutely absurd amount of possibilities, an absolutely insane amount of numbers. And with that, we're forced to make a lot of approximations. So, tomorrow, at last, well, yeah, I'm pretty much done anyway. Tomorrow, at last, which is going to be the final episode of the series, we're going to be talking about the more practical side of things. How do we apply this to reality? We're going to go a little bit more in depth on the approximations, and especially the approximations that allow us to actually use quantum mechanics to describe everything in the universe that isn't hydrogen. So we'll save that for next time.